All right, you can go.
Okay, so my project is basically synthesizing political opinion data. The usual political opinion surveys contain a lot of questions on people's demographical information and their ideology or party affiliations. The wealth of the information oftentimes leads to disclosure risk. And my goal of this research is to basically reduce the disclosure risks in the dataset while preserving the important relationships between one's demographics and their political ideology. So the dataset I use is AP VoteCast. It's a survey of the American electorate conducted in, I'm sorry, my video has been blocking my site, sorry. Is conducted in 50 states by the University of Chicago. There are roughly around 140,000 respondents, and the questionnaire contains more than 220 questions. So basically, for my synthesis project, I did it with a random sample of 1,000 observations, and I saved the 8 most important categorical variables, which are state, religion, sex, age, race, education, income, and ideology. And I used sequential synthesis to, in the process, basically I first, like I talked about before, I first synthesize age, sex, race independently. For variables age and race, I use the Dirichlet multinomial models, and for sex, I use a binomial model. And then I use the 3 synthesized variables to use them in the synthesis model for education, which is a multinomial logistic regression model. And then the income, which uses the synthesized age, race, sex, and education. And finally, ideology, which is synthesized with all the synthesized variables above. And these are basically my models for sex. For each observation, it is a Bernoulli trial, and for race and age, education, income, and ideology, there are all multinomial models. While for age and race, I use the Dirichlet priors, whereas for education, income, and ideology, I use explanatory variables in the logistic regression. Yes. And so after I synthesized the data set, I measured the identification disclosure risk in the synthetic data set, found an expected match risk of 1, which means that there's an average 1 out of 1,000 probability for each record to be correctly identified. And the true match risk is 0.001, which means that among 1,000 observations in my data set, there is 1 correct unique match. And with a false match risk of 0.917, it means that among the 12 unique matches, 11 of them are false matches, which indicates pretty low identification disclosure risk in my data set. And now on to utility evaluation. First of all, I basically, to examine the extent to which the synthetic data set resembles the original one, I was thinking visualization could do like a first step job to check how well the process preserves the distribution of our key variable, which is the political ideology, like among different demographical variables. And for The following are some graphs, and to compare the original data set with the synthetic one, I just like paired them together. And so this is the original distribution between etiology and age. And this is my synthesized one. We could see that some group has been higher, but the overall trends are similar. And this is between etiology and education. This is the original data set, and this is the synthetic one. You could see that a lot of because some education groups have been shrinked during the synthesis process, there is some variations between like the two graphs. And this is between etiology and income. Here we could see that the rich group has been enlarged in my synthetic data set. That's why it's been the bars have been significantly higher in the synthetic data set. And this is for etiology and race. I'm glad that my synthetic data set preserves the distribution preserves the makeup of different races, and the survey has been distributed among a heavy group of white Americans, and we could see that my synthetic data set does preserve this heavy race group, but instead of being more skewed to the liberal side in the original data set, it now has been skewed to more conservative ones, or like moderate to conservative. And after the group comparisons, I calculate the average absolute difference between the groups. So basically the calculation is just we plot the tables between two variables, and then we subtract we take a subtraction of their difference, and then we take it over the original proportion, and then we calculate to what extent the synthetic data set, the groups have been deviated from the original ones. And we could see that the table shows the average absolute difference, and we could see that the table of age per education has been displayed the most variation from the original one. But overall, I would say this is a pretty good synthesis. And I also did the global utility evaluation for my data set, and the propensity score is roughly 0.03, and cluster analysis is also, the score is also pretty low, as well as the empirical CDF score. So they all show like high resemblance between the synthetic data set and my original one. And as some concluding thoughts, first, a research recap. I basically employed sequential synthesis to synthesize the data set, and I found low disclosure risk and generally high global utility despite some compromises in the analysis specific utility. And one of the most important limitations in my study is that because I want to increase the speed of the computation, I only synthesize part of the variables and a sample of the entire data set. If this process could be employed in the entire data set, we could see like a higher disclosure risk in the evaluation. But I would also say we could see higher utility because as we have more information in our synthesis process, we could better update our priors. And also my risk evaluations are limited to only measuring the identification disclosure risk. I have not checked, explore more into the so associate disclosure risk. So yes, that could be done in the future. And that's all.
Okay, thank you, Maggie. And,